Our today's topic is uh, osmosis and osmotic pressure. Uh, and this is chemistry 12th. Now, osmosis, as you know that this it is the movement of the solvent molecules from a solution at low concentration to a solution at high concentration through a semi-permeable membrane. Now, what is this semi-permeable membrane? A semi-permeable membrane is a membrane which allows only solvent molecules to pass through. It does not allow solute molecules to pass through it. These semi-permeable permeable membranes we see commonly in case of cells, plant cells and animal cells. Now, these artificially these semi-permeable membranes can be also made in laboratories in the laboratory by depositing a thin film of gelatinous precipitate of copper ferrocyanide. Now, the phenomena of osmosis, it can be understood if we take 2 eggs and dissolve the harder shell of these eggs by putting them in a dilute HCl, and then if these 2 eggs are put separately in 2 beakers, one containing water and another containing a saturated solution of sodium chloride. Now, the egg which is put in this water, it gets swelled. So that means this swells this egg, whereas the egg which is put in saturated solution of sodium chloride, it gets shrunken. Now, why is it so? This is because in this case the egg which we have put in water, here osmosis takes place. Water gets into this egg through its membrane, as a result of which it becomes flaccid. On the other hand, in this case we see since we have put the egg in a saturated solution of sodium chloride, the concentration of the solution being higher, water will come out of this egg through its membrane, as a result of which its size gets shrunken, or it becomes less flaccid. So here we see exosmosis takes place. That is the movement of this solvent molecules it takes out of this egg, whereas here we see water molecules, they get solvent molecules, they move into the egg. So this is the case of endosmosis. Now we can also understand this phenomena of osmosis by taking a funnel and tying a semi-permeable membrane to its mouth, and when this funnel is filled with a sugar solution or any salt solution, and it is then put in an inverted position in a beaker containing water, again we see water molecules will move into this funnel through this semi-permeable membrane which has been tied, or which has been fitted to its mouth. Now this funnel, as we see here, it is put in an inverted position. So as a result of this osmosis, when molecules of these water molecules, when they move into this funnel, and the level of this solution in the system of this funnel, it will rise up. So this shows that osmosis has taken place. Now as a result of this osmosis, we see that a hydrostatic pressure gets developed on this solution, and this hydrostatic pressure which is developed on this solution as a result of osmosis, or as a result of movement of solvent molecules into this solution, it is known as the osmotic pressure. Now we can also define it as that when this phenomena of this osmosis continues, and this pressure, the hydrostatic pressure which gets developed on this solution, and we see the level also gets raised. Now a stage comes when no more osmosis takes place. That means a hydrostatic pressure is developed on this solution. So that means when this stage is reached, that means when equilibrium stage is reached, no water molecules move into the solution through this semi-permeable membrane. Now we have got a best apparatus for determination of this osmotic pressure, that is this Berkeley's and Hartley's method. Now this method is used for determination of the osmotic pressure of a solution. Now it is based on the principle that when a pressure is applied on a piston, the phenomena of osmosis can be stopped, or we can stop this osmosis as a result of applying external pressure on the piston. Now this the apparatus they used by Berkeley and this Hardy, it consists of porous part, the walls of which are made semi-permeable by depositing a thin film of a gelatinous precipitate of copper ferrocyanide. Now this porous part, one end of this porous part, it is connected to a water reservoir, whereas this another end of this porous part, it is connected to a long capillary tube. Now this porous part, it is fitted into an outer cylindrical metallic tube, which is fitted with a piston and a pressure gauge. Now this porous part, this is filled with water, whereas a solution of sugar or sodium chloride is put in this outer tube, to which this piston and this pressure gauge is fitted. Now when osmosis takes place, water molecules from this porous part, they go into this solution, into this outer tube through this semi-permeable membrane, which has been made artificially by depositing this copper ferrocyanide into its walls. Now as a result of osmosis, we see that the level of the water molecules in this capillary tube, it gets lowered. Now this shows that water molecules that have passed into this solution through this semi-permeable, artificially prepared semi-permeable membrane. Now as a result of this osmosis, a pressure gets generated, or a hydrostatic pressure is developed in this solution. This hydrostatic pressure, which we call as osmotic pressure. Now when we apply when pressure is applied on this piston, we can stop this osmosis. And the pressure that this is we put some weight on this piston, which is fitted to this outer tube. Now this pressure, the external pressure which we have applied so as to prevent the diffusion of water molecules into this solution, can be directly read from the pressure gauge which is fitted to this outer tube. Now this osmotic pressure, as we know, it was according to Van 't Hoff, it is a qualitative property. Van 't Hoff in 1887, he studied the osmotic pressure of a number of dilute solutions or ideal solutions, and he concluded that the osmotic these ideal solutions or the dilute solutions, like these ideal gases, they also obey different gas laws. But the osmotic pressure, it is according to Van 't Hoff, he said that osmotic pressure, that is, it is designated by pi, it is directly, or it is equal to CRT, where C is this molar concentration of the solution, and R is the gas constant, and T is the temperature. Or we can also put it like this, that means when that pi is directly related to C, that this is the case when temperature is constant, R is also constant. Now pi being equal to CRT, C being the molar concentration, R being the gas constant, and T is the temperature. So C being the molar concentration, it can be defined as the number of moles of the solute dissolved per liter of the solvent. So we can write here pi is equal to NB over V into RT, where NB is the number of moles of the solute, Now NB is equal to mass of the solute divided by its molar mass, or pi is equal to WB over MB V into RT. Now we can write MB is equal to WB over V uh, over V into pi into RT. So we can find out the molecular mass of a solute with the help of this osmotic process. Since this osmotic process is it is a qualitative property, so we can find out the molecular mass of a solute present in the solution. Thank you very much.